The force on a wire carrying a current perpendicular to a magnetic field is given by the following relationship. F equals B times I times L. This equation describes the motor effect, the phenomena of a wire experiencing a force when it carries a current through a magnetic field. In this equation, F represents the force the wire experiences in newtons. Then B is the magnetic flux density of the field the wire is in. Remember that this is a measure of how strong the field is, and we measure this in Teslas. The stronger the field, the stronger the force will be. Next, I is the current, which will be in amperes. A larger current will lead to a larger force. And lastly, L is the length of the wire which is in the field. The more of the wire there is in the field, the more of the current will be as well, which leads to a larger force. We should measure this length in meters. Otherwise, we won't be able to calculate a force in newtons. Let's see how we'd identify these variables in a simple motor effect demonstration. Here we have a wire carrying a current in this direction. Then we have two bar magnets either side of it, creating a magnetic field in this direction. Importantly, this setup means the current is perpendicular to the field, which is required to use this equation. Technically, we could adapt the equation for when these are at any angle to each other, but you won't need to know about this at GCSE. The field and the current will always be perpendicular in any examples you'll encounter. Then we would measure this as the length L. Notice we haven't measured the whole wire, only how much of it is in the field. In an exam question, though, you can assume a wire is completely in a field unless told otherwise. Then F represents the force the wire would experience. In this case, we can use Fleming's left-hand rule to determine that this force would be directed out of the page. Doing calculations with this equation comes up very frequently in exams, so let's try a practice question for this. The wire below, of length 40 centimetres, carries a current of 20 amperes to the right, perpendicular to an upwards magnetic field with flux density of 0.02 Teslas. Calculate the magnitude and direction of the resulting force. So we've been shown an image of the wire, but it hasn't been labelled. So step 1 is to draw a diagram for the question. This will help us understand what values we have or haven't been given, as well as the directions of these. So we're told that the current points to the right, and the magnetic field is perpendicular to this, pointing upwards. We can also assume the full length of the wire is in this field. You don't have to do this step, but it's helpful for getting a grasp of the situation described in the question. There may also be a labelled diagram already given for you. In step 2, recall the equation for the force on a wire. This equation for force is that force equals I BL. That's current times flux density times length of wire. Remember that to use this equation, the current should be perpendicular to the flux density, which is what's happening in our diagram as the wire is perpendicular to the field. In step 3, substitute the values in the correct units. So substituting the values from the question gives us that the force is equal to 0.02 times 20 times by 0.4. Here the flux density and the current were in the correct units of Teslas and amps, but the wire was in units of centimetres, so we've had to convert 40 centimetres to 0.4 metres. Putting this in our calculator, we find that F is 0.16 newtons. This is the magnitude of the force, but we still need to find its direction. In step 4, use Fleming's left-hand rule to find the direction. Remember that this is when we hold our left hand with our thumb, index finger and middle finger all perpendicular to each other, with each finger representing a different direction in the motor effect. In this case, we would hold our hand out like so. The middle finger represents the direction of the current, and the index finger is the direction of the field. With our hand like this, our thumb is pointing towards us, which we represent with a dot like this instead of an arrow. The thumb represents force. So in this diagram, the force would be directed out of the page. Now let's clearly state our final answer. So in step 5, write out the complete solution with the correct unit. So overall, we found that the magnitude of the force was 0.16 newtons. And this was directed out of the page.
Thanks for watching. If you want to take your GCSE revision to the next level, head over to launchpadlearning.com and check out our smart learning platform that's been designed to get you top results in your exams. We cover your whole specification and make revision fun with interactive quizzes, easy to follow videos and more. You'll be kept motivated by your own AI tutor who's here to support you every step of the way. To check it out for yourself, click here. Or click here to keep watching a selection of the videos from our full GCSE Physics course. See you there!